All right, shall we get started?
Cool.
Okay, welcome everyone. So we're up to proposition 25. I'll start. I guess maybe we're going to split proposition 26 into a couple of cases that we'll take individually. So proposition 24, maybe I'll remind you. So proposition 24 said that if two triangles have the two sides equal to two sides respectively, but have one of the angles contained by the equal straight lines greater than the other, they will also have the base greater than the base. So we're talking about the relationship between side lengths and the angles that they subtend. And proposition 25 is basically a direct consequence of proposition 24. It says if two triangles have the two sides equal, to the two sides respectively, so A, B, C, and D, E, F so I'm still writing the statement, but I'll do the translation into sentences that involve letters of the vertices as I go along. So suppose AB is equal to DE and AC to DF. So that's what I said so far. But have the base greater than the base. So that is the base of one triangle greater than the base of the other. And let BC be greater than EF. They will also have one of the angles contained by the straight lines greater than the other. I think this statement is definitely a bit less precise than one of the angles is what you mean is the one corresponding to the greater base, right? So we claim BAC, the angle BAC, is greater than angle EDF. Okay, so here's the proof. Well, these two angles are either equal or one of them is greater than the other, right? If not, BAC is either equal to EDF or is lesser. If it is equal, then by proposition 4, BC would be equal to EF, but it is not. Okay, so BAC is not equal to EDF. If BAC is less than EDF, then by what we proved last time, so proposition 24, implies BC is less than EF, which it is not. So we conclude that the only possibility remaining is the one that we claimed, namely that BC BAC is greater than EDF. So, I mean, this is just bookkeeping. It's a direct consequence of proposition 24. Any questions? Okay, so let's move on to the next board and proposition 26. So I wouldn't say these two propositions are very interesting. They're just filling in kind of obvious consequences. Proposition 26 is kind of long, but not very interesting, unfortunately. Alright, so what it says is the following. If two triangles, maybe I'll draw them first. ABC, DEF. If two triangles have the two angles equal to two angles respectively, so let's say ABC is equal to DEF and ACB is equal to DFE, and one side equal to one side, namely, so there's two cases, namely either the side adjoining the equal angles, so I'll just annotate that as case 1. So case 1 is where BC is equal to EF. Or the other case, that subtending one of the equal angles, or that subtending one of the equal angles. So that's case 2. So that would be, say, AB is equal to DE. The point being that you should take the side that matches with the, I mean, two angles equal to two angles means the situation that I've drawn here, and you should have the sides matching that correspond to the equal angles. That's part of the statement that's a bit hard to say properly without introducing the symbols. And the conclusion is that the remaining parts of the triangle are the same. They will also have the remaining sides equal to the remaining sides. And angle to the remaining angle. Okay, I guess I'll do the first case, Kenneth, and you can do the second.
Sounds good.
Okay. All right. Okay, so in case 1, BC is equal to EF. And what I need to show, so we assume BC is equal to EF, and need to show AB is equal to DE, AC is equal to DF, and angle BAC is equal to angle EDF. Okay, so let me start with proving that AB is equal to DE. For if AB were not equal to DE, one of them is greater. And the situation up till now is symmetric, so I may as well assume without loss of generality that it's AB. Okay, moving on to the next board. And I've assumed those are equal in case 1. Okay. But if AB is greater than DE, well, let BG be equal to DE. So introduce G here with BG equal to DE. I can do that by, oh, actually I forgot what proposition this is. Let me just find it. Yeah, proposition 2. And join GC. Okay, since BG is equal to DE, and BC to EF, oh, I can't hear you. Hello? You're really soft. Maybe I'm too far away from you. Hello? Yep. So BG is equal to DE and BC to EF, and there's a common angle. So those two triangles are congruent by proposition 4. In particular, GCB is equal to DFE. But that's a contradiction because that's a part equal to the whole. Right, so that would mean GCB, well, GCB being equal to DFE, DFE is by hypothesis equal to BCA. And that can't happen. Okay, so this shows that AB, in fact, must be equal to DE. And by a similar argument, we show that AC is equal to DF, and then we're done, right? So we've shown AB is equal to DE, AC is equal to DF, and we have these triangles. I don't think there's anything left to show, right? So by proposition 4, the angles are all equal. So that concludes case 1. All right, hand it over to you, Kenneth.
Cool, thanks, Dan. This is probably one of the longest proofs that we've done. I should attach a speaker.
Yeah, that's right.
Can you hear me?
Yeah,
I'm going to attach a speaker, so
yep, there you go.
I'll get closer to the orb. You guys are all crowding around the orb. I can't.
There's too many ghosts.
Wait, why can't I? Am I? I'm still attached. Got it. All right. So I think Dan's done most of the heavy lifting for us. The other case, just going to be basically reducing it to the first case. So I'm going to redraw the diagram because we're going to have to mark slightly different angles and size and so forth. So let me just redraw the diagram here. So two triangles, ABC and the DF. Let me just label these ABC and DEF. And the same assumptions, right? These angles are the same. These angles are the same. But the side assumption is that instead of assuming that the angle joining or containing the line that belongs to both angles are the same, we're going to assume that one of the sides out here, not the one between the angles, are equal. So we're going to assume. So I guess the conclusion is that given these things are equal, we're going to have to show that these two triangles are the same, right? Congruent, all the sides are equal, and all the corresponding angles are also equal. So we're going to assume that BC is greater than EF, right? Without loss of generality. And basically, we're going to do some arguments to show that this is not true, and then thus reducing it back to case one, which is already done by Dan. So by proposition 3, right, we do the usual thing of constructing a point on a line which is lesser, or the longer line, right, of the two things that we've assumed to be not equal, and go from there. So we're going to construct a point H on BC such that BH is equal to BEF, right? So we're going to mark it in the diagram, H on BC, right? So we're going to drop a line from here to here. There's an H here such that the lengths BH, EF are the same, right? So these two are the same. Okay, so we're going to go back to our trusty proposition 4 to show that triangles are the same, right? So since I keep doing this, trying to write with the straight lines.
Yeah, we should
So
change the interface.
we're gonna, or I should just rewind my brain, right? Which is
Well,
easier to do than
at
changing
that
the
at that
interface.
point, I think you can blame the computers rather than you. Yeah.
So since BH is equal to EF, so since I'm telling you that I'm going to be applying proposition 4, which is really, two sides being the same and an angle being the same, showing that two triangles are congruent, I'm going to be listing some sides that are equal and an angle which are equal, right? AB is equal to DE, all right? Why is that? So BH and EF are the same by construction. AB being the same as DE is by assumption, right? We assume this. And finally, the angle ABC is equal to angle DEF. This is also by assumption. This is a blue angle, right? By proposition 4, we have shown that the triangles ABH and DEF are the same. The triangles ABH, so the one we constructed, and DF are the same or are equal. All right, so this means all the angles are equal, the sides are equal, and so forth, or the corresponding angles and sides are equal. In particular, all right, so in particular, AH, which is the red line, is equal to DF. And a bunch of other angles are equal, right? Angle BAH is equal to angle EDF. And finally, the third thing that's equal is the angle BHA is equal to angle EFD. Okay, but angle EFD is equal to BCA. BCA, all right, why is that? So EFD is the one that's marked red, angle BCA is the one that's marked red. So that's by assumption, we assume that these were equal to start with, and we're going to derive contradiction from this. And since angle BHA,
Sorry,
right, so
to be a little pedantic, I think you said out loud that those two triangles are equal. You wrote and mean that the two angles are equal. Maybe I misheard you, but just to be clear that we're not actually presuming what we're trying to prove. So you mean the angles are
yes,
equal?
you're probably right, because when I'm doing, I have no idea what I said. Yeah, sure, sorry. And since BHA, I'll mark it here. So this is BHA, this is that one that I'm talking about. Is greater than BCA. sorry, I skipped the line. BHA is external to triangle AHC. It is external to triangle AHC, right? So then we can use proposition 16 to remember proposition 16 tells us that the external angle has to be bigger than the angles on the opposite sides of a triangle, right? So by proposition 16, right, angle BHA is greater than which one? Well, it has to be the one that's marked, right? So ACB or BCA, I guess. I'm using consistent notation here. BCA, right? So this is impossible because we said they were equal, right? So this is impossible, all right? So BC is equal to EF, right? Which is the assumption that we started with being false. So if that's false, then BC and EF must be equal. So so this case follows from case 1. Cool.
Nice. I don't know if your version of the book, it doesn't actually like reduce it to the first case. It just repeats the proof, basically. I don't know. I mean, you can.
Yeah, it did. I just saw in my notes that basically the same. So I'm like, well, you already did it. So
Yeah, that's right. I think that makes sense.
yes, in the book they don't refer back to case 1. They don't even have cases. They just kind of do the proof one after another without referencing the previous part, right?
I had to look a few times to figure out where the division between the two cases was. Cool.
Yeah, wall of text.
Yeah, that's right. Yeah.
Cool.
Any questions?
Yeah, I was wondering about, so earlier, Dan, you had said without loss of generality, and then somewhere else you had said, like, similarly. Like, does Euclid have these notions of without loss of generality, or does he use some other phrase for it?
Let me see. Okay, so for the place where I said without loss of generality is where if AB is unequal to DE, one of them is greater. And then he says, let AB be greater, blah, 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 blah. And he just never addresses the other possibility, I think. At least in the translation. Let me check. Yeah.
I mean, strictly speaking, I should say that without loss of generality, we can assume BC is greater than EF because showing that that's false just means that the reverse inequality with the equal sign is true, right? But then, right, I was a bit cavalier with that.
Yeah, it's an interesting. I think he's leaving that to the reader to recognize the symmetry and notice. I think that's my feeling is that that's what the word "let" is doing. Right, so you can just say "let something be something," as I mean that's kind of introducing a sub-part of the argument, and then by basically leaving the rest of the argument empty, he's implicitly asserting that that's the whole argument. Yeah, but he doesn't say anything directly like what I said. That's true. That was an elaboration of ours. And what was the other question about similarly? I think that is actually he actually says. Yeah, that's right. So that part is actually something he mentions. Yeah.
Thank you.
Other questions? Okay, cool. So I guess we'll move on to the singular learning theory session. I'll note one interesting new twist here is that when we erase these boards, they continue to live in a history world, which you can access by the history portal, which is over behind, just over here where I'm walking in that direction. So I'll erase these boards now, and of course you should stay for the singular learning theory session, but if you can't restrain your curiosity, you can hopefully find these boards in there.